A fresh bag of cement contains a highly volatile, dehydrated chemical binder seeking equilibrium. The exact moment a single drop of water hits it, the dry powder reacts violently and begins to crystallize. This reaction defines a hydraulic material. Cement only activates its cohesive and adhesive properties, the ability to bind sand, gravel, and steel into concrete, strictly in the presence of water. This table details the difference between hydraulic and non-hydraulic cement. A non-hydraulic binder, like plaster of Paris, is derived from calcined gypsum. Its products of hydration are not water-resistant, meaning it cannot maintain chemical stability if exposed to moisture after it sets. Joseph Aspdin invented the modern hydraulic variant in the United Kingdom in 1824. He patented it as Portland cement. This is not a corporate brand name. Aspdin chose the title because the set material's gray color closely resembled the natural building stone quarried here, on the English Isle of Portland. Because Portland cement is a chemically active, water-seeking binder rather than a simple aggregate, civil engineers must strictly control its every step. It is governed by standardized weights, derived volumes, and rigid environmental isolation protocols. The global baseline for these controls begins with the standard packaging unit, the 50-kilogram bag of cement. That exact weight masks a counterintuitive physical reality. When you look at a full bag, approximately 40% of its internal volume is entirely empty space, or voids, trapped between the powder particles. Civil engineers must account for this empty space when designing concrete mixes. By factoring in these voids, the standard density of raw cement is established at exactly 1,440 kilograms per cubic meter. To use this material on a job site, we must convert its fixed weight into a usable volume. We divide the 50 kilograms of a standard bag by the standard density of 1,440. This gives us the standard volumetric yield of a single bag, exactly 0.0347 cubic meters, which translates to 34.7 liters. This chart lists unit weights for common construction materials, revealing a stark numerical contrast. Raw cement sits at 1,440 kilograms per cubic meter, but once hydrated and mixed with sand and aggregates to form plain cement concrete, the density leaps to 2,400 kilograms per cubic meter as those internal voids are filled. The 50-kilogram weight is a precise mathematical anchor. It ensures that whenever a crew mixes concrete, they can reliably calculate exact volumetric ratios without having to manually weigh the powder in the field. Establishing the physical volume of the bag is only half the equation. To understand how the binder actually works, we have to examine its microscopic chemical recipe. This table outlines the two mandatory categories of raw materials in cement manufacture. First, argillaceous materials provide silicates and aluminates, sourced from slag, slate, shale, and clay. Second, calcareous materials provide calcium, sourced from limestone, marl, and chalk. Inside a manufacturing kiln, these base materials are burned at extreme temperatures to break them down into a highly specific oxide profile. The heaviest and most critical component of this profile is lime, or calcium oxide. By standard design, lime must constitute roughly 62%. Together, lime and silica account for 84% of the volume. While lime dictates the final strength, silica dictates the timeline. It controls the setting action of the paste. If a manufacturer includes too much silica, the concrete will take significantly longer to harden. The vast majority of a cement bag's chemical payload is dedicated to executing just two tasks: ensuring the structure gets hard enough to carry a load, and ensuring it takes the correct amount of time to get there. If 84% of the composition secures the strength and the timeline, what purpose does the remaining 16% serve? This table shows modifiers. Alumina, at 6%, is an accelerant for quick setting, but excess alumina lowers structural capacity. Further down, iron oxide averages 3%. It acts as a fusing agent to bond ingredients in the kiln and gives cement its gray color. The final fractions contain trace elements like magnesia, soda, and potash, byproducts introducing vulnerabilities. If these alkalis exceed strict limits around 1%, they react with the environment. This manifests as severe cracking and efflorescence, a destructive white staining on the finished concrete. The chemical equilibrium inside that 50-kilogram bag is incredibly fragile. Every modifying oxide introduced to make the manufacturing process cheaper, or the setting process faster, opens up a new vector for structural failure. Because this finely tuned oxide payload is deliberately designed to seek out and bind with water, it is highly reactive to even trace amounts of ambient moisture. The moment a bag leaves the factory, the atmosphere begins attacking it. To slow this inevitable chemical degradation, civil engineers enforce rigid isolation protocols for large-scale storage logistics. Under Standard IS 4082-1996, warehouses are structured specifically to fight moisture. The first line of defense is vertical separation. Bags must be stacked strictly off the floor on wooden piles, maintaining a clearance of 150 to 200 millimeters. This breaks the capillary action that would otherwise draw ground moisture directly up into the bottom layers. Next are physical pressure constraints. Stacks cannot exceed 10 bags in height. If piled higher, the sheer downward force causes the bottom bags to undergo compaction, lumping up into hardened, unusable blocks under the pressure. Finally, spatial constraints govern the layout. Stacks are limited to no more than 3 meters or 4 bags in width, and they must be kept strictly away from exterior walls. This ensures adequate airflow and prevents ambient moisture from becoming trapped in dead zones. These warehouse protocols serve as a physical blockade, pausing an inevitable chemical reaction until the material reaches the job site. Even with perfect compliance to IS 4082, standard Portland cement possesses an aggressive biological clock. It cannot be stored indefinitely. This table quantifies the chronological decay of cement's 28-day compressive strength. When fresh out of the factory, it operates at 100% capacity. But look at the 3-month mark. After just 90 days of sitting on a shelf, its efficiency drops to 80%. The exact same volumetric mix, handled by the exact same crew, will now yield a structure with 20% less load-bearing capacity. Over the long term, the degradation curve accelerates. At 12 months, the powder retains only 60% of its intended strength. By 24 months, it has dropped to 50%. At this stage, half of the active chemical payload has already reacted with atmospheric moisture, resulting in a compromised chemical product that shares few properties with fresh powder. Mastering cement requires moving beyond simple weight and volume calculations. It demands a rigorous understanding of the precise chemical payload hidden inside the bag and an acute awareness of the relentless way time and the environment degrade it.